Hi guys, welcome back to my channel, and today I'm going to be showing you guys an editorial for the third problem in the AtCoder DP problem set, vacation. So here, a vacation that has n days, and each n day you can choose activity A, B, or C. And for each day I, these have AI points of happiness, BI points of happiness, or CI points of happiness. And the main constraint here, which makes the problem interesting, is that you cannot pick the same activities for 2 or more consecutive days in a row. And at the end, you want to find the maximum total points of happiness that our character Taro is able to gain. So let's look at this first sample here. Well, how would we figure out the best way to do the vacation methodically? Obviously, you can do this in brute force, but that would take way too long because there's too many combinations. So how would we do that efficiently? Well, let's say we are going to pick activity B on the second day, which is this 50 here. How do we figure out the maximum happiness that he can gain up to this point? Assuming we take B on the second day, and assuming that that's all we want to calculate, so nothing after that matters, what's the maximum we can calculate for this value? Well, this depends on what you choose. If you choose either activity C the day before or activity A the day before, because you're not allowed by the problem statement to choose activity B. So here, the maximum happiness you can derive here is 120, because you can pick 70 first, and then after that, choose 50 here, because 10 is simply less. Okay, so now we have this information. So how can we use this to solve the full problem? For this 50 here, we know that the maximum you can gain, assuming you take that, is 120. So let's calculate it for the rest of them. Obviously, for the first row, there's nothing before that to affect it. So the answer for 70 is simply 70. Now for 80, you can either come from B or from A. So the maximum, assuming you take B last, is just 120, which is 40 plus 80. This is also 120. Now, if I pick activity A on the second day, either you can come from activity B, which is worth 40 happiness points, or from activity C, which is worth 70 happiness points. So obviously, you would take 70 because it's greater. So now our value here would be 90. So now, since we have all of these values, essentially this row here doesn't matter for calculating the rest of our problem, because we already know all of these values, which is the only thing that can affect it. Now for the final row, we don't have to mind trying anything else than these values, because these values are the maximum given you've taken each of the respective activities as the final activities. So for assuming we take activity C on the last day, this will be affected by this activity B on the previous day and activity A on the previous day. So all we do is take the max of these two values, which is 120, and add 90 to it, which makes it 210. Okay? Now that we have it for 90, let's calculate for the rest of them. 60, this one depends on 80 and 20. The max of those is 120, and 120 plus 60 is 180. Now for 30 depends on B from the previous day and C from the previous day. Both of these are the same, so the max is 120. And plus 30, assuming we take activity A on the last day, means that assuming we take activity A on the last day, then the maximum happiness that Taro can have is 150. And now, finally, we just take the max of all of these to find our answer, which is 120. Now, the complexity of this is just 3 times n, because for each of these, we just have to query 2 values from the past, and so that's our O(n) time. And obviously, we have to store all these values. So that will also contribute to the complexity. And as you can see, that will pass the constraints very nicely. So how do we put this idea now into code? Well, as some of you might be able to tell, this is, again, a nice use for DP. If we have DPI, which is the day, and DPJ, which is A, B, or C, for the last activity taken, then this is the max of the DP I minus 1 and whatever is not J. So for example, if J is A, then this would be B here, and the max of DP I minus 1 for the other one that is not J. So for example, if J is A, then this would be B and C. And for this, you just add the happiness of from row I of J. So here we have a very simple recurrence relation. And as you can see, this looks very recursive. You can very simply implement this as recursion, but the solution, the code I'll be showing you is iterative because often doing it iteratively is faster. So let's look at here. First, we input it. ABC is just the happinesses for A, B, and C. And for the first row, as discussed, there's no confusion because there's only one thing affecting it. For 10, if I assume I take it, then the maximum happiness is just 10 because there's nothing before it. And now we permeate this through. In this particular solution, instead of going from DPI and J backwards, you actually go from DPI, J, and go forwards. So as you can see here, I is the day, okay? It's the day. J is the last taken activity. And K just cycles through the activities that aren't J, so we can put it forward. So I can see DPI plus 1 of K is just the max of whatever it is currently, which would be given you take the other option, which isn't J, and of given if you have J before it, plus the happiness of this activity K on the I plus 1 day. So as you can see, this is basically just the reverse of this. And after we finish filling in this DP array, we just take the max of the 3 ends, and that's our final answer. So I hope you guys found this helpful and learned some more about DP from it. If you liked the video, please like, share, and subscribe, and stay tuned for the rest of the editorials. I'll see you next time.